Welcome to Cloud on Air, live webinars from Google Cloud. We're hosting webinars every Tuesday. My name is Lak Lakshmanan, and I'm going to be talking about a development workflow when you're building end-to-end machine learning models with TensorFlow on Google Cloud Platform. You can ask questions anytime, and we have Googlers on standby to answer them. So this talk that I'm going to be doing is basically going to be walking through a set of code labs. And the code lab is here on that link, and it's essentially about building an end-to-end machine learning model. We'll walk through all of the steps in order to do that. But before we do that, let's talk a little bit about what machine learning looks like on Google Cloud. So what we're going to be doing is that we're going to be using distributed TensorFlow on Cloud ML Engine. And when you look at TensorFlow, you have a varying levels of abstraction levels, with the bottom level essentially being how you run core TensorFlow in C++. But more commonly, people do core TensorFlow in Python, which essentially calls the C++ API to get high performance on a variety of different devices, whether they're CPUs or GPUs, etc. The level at which we will be working at will be tf.estimator. This is this very high-level, out-of-the-box API that handles distributed training for you. So why do we talk about distributed TensorFlow? Well, when you look at a lot of machine learning frameworks, they can handle what I call toy problems. Toy problems are problems where the input fits into memory. Well, you take your data, your inputs, you train your model, and you have your model. Right? And if all you have are small data sets, then that's fine, and that's what I call a toy problem. But in order to build effective machine learning, you need three things. And the first and foremost thing that you need is large amounts of data. And if you have big data, if you have large amounts of data, then batching and distribution become extremely important. You need to take your inputs, and you can't read all of them from memory all at once. You have to break it up into chunks and read them. You can't go ahead and train your model all on one CPU or GPU. You often have to distribute to multiple compute nodes. And once you have batching and you have distribution, and this is something that you need when you have large data sizes, then TensorFlow starts to play a huge role. Okay? The other thing that you need when you want to build effective machine learning is that you need what's called feature engineering. This is where you don't use the raw inputs as is, but you take your raw inputs and you do transformations of them. You may pre-process those inputs, you may create features, and we look at examples of those, and it's on those features that you train your model. And the reason to do this is that the raw data, it can be pretty noisy, can be relatively hard, and may take many epochs and a much more complex model for the model to learn from the raw data, where if you've done feature engineering, it might be easier for your model to learn. So the third thing that you need when you want to build effective machine learning is that you need to be able to experiment with a variety of different model architectures. And that's another place where TensorFlow comes in extremely handy, because it is the most popular tool for deep learning. And importantly, it's very popular both among researchers and among developers. So what that means is that when you're developing with TensorFlow, you get the benefit of essentially being able to build models that are leading edge. And you get to do this often by basically taking open source code and applying it to your data. So that's essentially what TensorFlow provides. But what else does a machine learning framework need to provide? Besides the ability to handle large data, the ability to do feature engineering, and the ability to experiment with model architectures. What else do we need? Well, one thing is hyperparameter tuning. Sure, you can train a model, but oftentimes you don't train a model, you train a family of models. And you want to basically go ahead and do this experimentation easily in an automated way, and that's where hyperparameter tuning comes in. Another thing that you may want to do is that once you have your model, you have clients you're accessing this model, and you need to basically auto-scale that prediction code so that if you have 100 clients or 1 million clients, your prediction API scales. And so you want your client code to be able to access your model not through Python, not through TensorFlow, but with just a REST API call, so that you basically are able to access this prediction model from pretty much any device, any language that you want. But then the question becomes, if the client is basically going to be making REST API calls, who's going to do all of the pre-processing and feature creation? Because your model, the model that you deployed, expects to see these new features. So who's going to do that? Because what the client wants to give is the raw data. And that's where Cloud ML Engine comes in. Cloud ML Engine helps you to basically do auto-tuning, helps you to scale out your predictions, and helps you maintain it in such a way that you get repeatable results between training and between prediction. Okay? So the way we go through the development workflow on ML Engine is that you start with Data Lab. And Data Lab is a Jupyter notebook that's hosted. So you basically start with Data Lab, which is a Jupyter notebook, and you do it on a small data set. Maybe you have a CSV file, you're doing your exploration in Pandas, you may be using Apache Beam, and then you're writing a TensorFlow model, you're improving it, and then you get a model that works. And once you have a model that works, you don't know how well it works. And the way you basically figure out how well it works is that you take it now and you scale it out to your entire data set. And you do that on Google Cloud, where you're basically using things like Cloud Data Flow to do your pre-processing, you're reading your data off cloud storage, and you're running your model on many machines using ML Engine. And that helps you on all of these things are serverless. You don't have to manage any clusters. You don't have to manage any infrastructure. So that's basically the end-to-end workflow that I'm going to be walking through. So we're going to start with how to take your data, explore it, visualize it, and then to create a smaller part of that data to play around with, to create your sample data set, and then to be able to develop your first TensorFlow model. And having gotten your model, you want to now try it out on the entire data set. So you go back and you create your training and evaluation data sets that are large, that are over the entire data. And having done that, you execute the training, this model that you have developed, you execute that training, you deploy it, and then you basically access it from other clients, for example, from a web application. So these are the 7 kind of steps in this. And this link takes you to the code lab and to the GitHub repository. So here's a code lab, and here's a GitHub repository that contains all of these notebooks. So that's notebook 1, that's notebook 2, notebook 3, etc., all the way. So we'll basically go ahead and walk through each of them one by one. So the first thing is to explore the data. Now, the model that I'm going to be doing is going to be a structured data model. And you might say, well, a second, you're doing structured data. Isn't that boring? Well, it's kind of boring, yes. Images and sequences get all the press. But even at Google, where we've been doing machine learning for a long time, MLP, multi-layer perceptrons, which are basically the kind of model that you use for structured data, that is nearly 2/3 of all the models that we have in production. LSTMs, which are sequence models, the kinds of things that you do for time series and for text, they're another 30%. The hello world, MNISTs of the world, the images, that's less than 5% of production models. So if you're starting out in machine learning and you're saying, what should I concentrate on? Where you start is with structured data. So that's where we're going to start. Okay? So our goal here is that we want to predict the weight of a newborn. So this is a healthcare data set. And the idea is that if you can predict the weight of a newborn, we can identify babies that may need special facilities, incubators, etc., and then get babies that care that they need. So the idea is that a pregnant woman walks into a doctor's office, and based on a variety of measurements that the doctor has, they want to be able to predict what the weight of that newborn is, which is a pretty good indicator of the health of the baby. Okay? So how do we do that? We need a data set, and the data set that we're going to use is an open data set collected by the US government. It's all the births recorded in the 50 states in the US. So this is called the natality data set. It's about 137 million rows, pretty reasonable sized data that we can use to demonstrate the kinds of things that we want to do. Okay? So this data set includes things like the birth, right? The date of birth, the location of the birth, also the baby's birth weight in pounds. This is going to be our label. This is the thing that we're trying to predict. And things like the mother's age at the time of birth, the gestation weeks, how long was the pregnancy? Was it a preemie pregnancy? Was it full term, etc.? So those are the kinds of features that we have that we can use as predictors to predict the weight of the baby. Okay? So first thing, to explore and visualize the data set. So if you go to the code lab link there, so number one is to explore the data. So we're basically going to go ahead and go into the Cloud Shell icon. Okay? So I already have that running here. So there it is. Here's my Cloud Shell. Okay? And in here, I can go into Cloud Shell. I can then basically run the first command, gcloud compute zones list, okay, which is here. So go down there, gcloud compute zones list. This tells me all the compute zones that are available, and you want to go ahead and pick a zone that's close by to where you live to reduce your latency and to basically have your compute in that particular region. The next step is to basically go ahead and create a data lab VM. Just to save time, I've already done this, so I'll skip that step. And the third thing is to go into the BigQuery console. So we can go to the BigQuery console by going into into the GCP console. Going down, let's go into the BigQuery. There is BigQuery. And once we are in BigQuery, we want to go ahead and compose a query, and the query that we want to compose is this. Okay. And we want to do this in standard SQL, so I'll just go ahead and do standard SQL. Another way to do this is to go into show options and turn off the legacy SQL query. So let's go ahead and do the standard SQL. That is the query that I want to run. So the query is that I'm going into this data set called public samples natality, and I'm basically picking up all the births that were between 2000 and 2005. Let me go ahead and run the query. And I'm basically going ahead and finding the plurality. The plurality is whether it's a single child was born, whether it's twins, whether it's triplets, whether it's quadruplets or quintuplets. So we see, for example, that single kids are obviously the highest. There were about 500,000, 500,000 or so twins, and about 28,000 triplets, etc. So that's the data set. And remember, this is a huge data set, right? 137 million rows. We were able to process it in about 4 seconds. Okay? So that's the power of BigQuery here. And we didn't create a cluster. We didn't set up any infrastructure. I just went into BigQuery and I said, this is the cluster I want. This is the query that I want to run. And at that point, thousands of nodes essentially processed my query for me. And that's why I was able to get back the results on this pretty large data set. I'm only picking 2 columns, or actually 3 columns, which is why only 3 gigs of data got processed. So BigQuery is a columnar database. It only processes the columns that your query actually references. And we're able to basically go ahead and get our results back. So let's go ahead into the next step in here. And so this is cool. I get my table. The table isn't very interesting. What we want are graphs. We're data scientists. We want graphs. So let's go into Cloud Data Lab. So this is Cloud Data Lab. Okay? And in Cloud Data Lab, let's go ahead and start a new notebook. And in that notebook that I have started, let me go ahead and take essentially a very similar query. So here's my notebook. I will go ahead and set up my query. And I'm basically importing the BigQuery package. And I'm basically getting df, which is a pandas data frame. And I'm going ahead and doing df.head, which shows me the first few elements of that data frame, just to make sure that we have something reasonable to plot. So this is essentially doing the same thing that we did on the BigQuery console, but I'm now doing it from Python, from my data lab notebook. Okay. And the next cell, we want to do this. So let's do this. Okay, so we see that we basically got a few of the rows, the weight in pounds, whether the baby was male or not, the mother's age, etc. But the next thing that I want to do is to basically go ahead and get the distinct values of a particular column. Is the baby male or is it baby female? And go ahead and do a bar plot. So let's go ahead and do this. So this is kind of where Python starts to come in really useful. So we can basically do all of our normal plotting that we do in Python, and we see, for example, that there are a few more male babies than there are female babies that are born. And this is the average weight. So this is essentially the male babies are slightly heavier than female babies. Okay. And we can also do the same thing for gestation weeks. So I'll go ahead and do this for gestation weeks. And notice that each of these things that I'm doing them pretty interactively, but each of this piece of lines of code are actually processing hundreds of millions of rows of data, right? So now we're basically seeing that there are, let me just make this slightly bigger. Okay, so with 17th week of pregnancy, 18th week of pregnancy, etc., you see that the weight of the babies tends to go up, and then basically once the babies get almost full term, it kind of evens out. Okay. So that's the first step. We've explored the data. We've kind of seen how the average weight, which is the kind of thing that we want to predict, how it varies with one predictor, in this case, the gender of the baby, and another predictor, which is the gestation weeks. How long has the pregnancy lasted? Okay. So let's move back to this. So that was the first step, to explore and visualize the data set. We did that with Data Lab using BigQuery. Okay? And having done this, we basically got graphs like this that said that, sure, the gender of the baby matters. Sure, the plurality, I did not show you this, but you could also do other columns in the data set. So in this case, whether it's a single child or twins, etc., twins tends to be a lower weight than single children, for example. So you can basically go ahead and do this and find which features matter. So having done that, we have now identified our predictors, and we are on to basically do the next step, which is to basically use to go ahead and create our data set based on those predictors that we have chosen. So to build a machine learning model, the first step is to create the data set. That is to go ahead and pull out the important predictors. We've now explored the data. We're ready to go ahead and create the data set. And to create the data set, right, we need to also think about one more thing. And the thing that we need to think about is causality. Will we actually know the sex of the baby and the plurality of the baby so that we can predict the weight of a baby? Well, we will if an ultrasound was carried out. We won't if there was no ultrasound. So what we need to do is we need to figure out a way to work with this partial data. Sometimes we know the data, sometimes we know the prediction, the predictor, and sometimes we don't. So let's look at how to basically create this sample data set in BigQuery. Okay? So here, we'll move on to step number 2 to create the data set. And there, I will basically go ahead in Data Lab. I will clone the notebook. Okay. So let's go down here. And in here, let's just clone the notebook. And this will essentially go to GitHub, pull in the code. And at this point, I can go into here. And I see my training data analyst. And in there, so this prevents it from having to copy and paste code every time. I can go into the directory that's pointed out. So this is the same GitHub repo that I showed you earlier. So deep dive, and this is the structured data. And in there, we're now on to the second of the labs. And in this lab, right, once a notebook comes up, you notice that there are 3 lines here about the bucket and the project. Those are in Quick Labs. So we'll go into Quick Labs and get the project ID and basically throw that in here. So that's my project ID. And the region is fine. And I need to go ahead and have a bucket. So let's just make sure that the bucket exists. So we can go down to the GCP console, go into storage, and once we are in storage, we see that yes, there is a bucket, and the bucket is actually the same name as a project, conveniently enough. So we can basically go down here, and it's essentially that, and we will basically use that bucket, and we can run that. We can run the next cell, and having done that, now we don't need to create it, the bucket's already there. And now we can sample the data set. So I'm just going ahead and running them one by one. You can click run here. What I'm doing is I'm pressing Shift Enter, but then now I'm grouping by the hash month and getting my training data. And once I have my training data, and I'll stop running through it because it's essentially the results are here, we can basically look at what the data set looks like. We can look at the weight in pounds, which on average is 7.2 pounds, but the standard deviation is about 1.3 pounds. The minimum baby was half a pound, and the maximum baby was almost 14 pounds. The mother's age, again, you have it, but notice something interesting. The weight in pounds and the mother's age, there are different numbers. Why would that be? Well, because sometimes you have missing data. And pandas doesn't count nulls, and so we have some babies in our data set for whom the weight wasn't recorded. We have some pregnancies, a lot of pregnancies looks like, for which the gestation weeks aren't known. So we need to deal with that as well. So what we are doing is that in our pre-processing in pandas, we make sure that the weight in pounds is greater than 0, that the mother's age is greater than 0, that the gestation weeks is greater than 0, and the plurality is greater than 0. So we're just filtering the data to make sure that we're only dealing with valid data sets. And then remember what we talked about, that sometimes you know it and sometimes you don't. So here's how we're dealing with it. We're basically taking the numbers 1, 2, 3, and 4, and 5 and replacing them with single, twins, triplets, etc. And we are basically going to simulate the lack of an ultrasound. So for every row in our input data, we'll create one more row. And the second row is going to be a copy of the first row, except the plurality is only going to be single or multiple. The idea being that we don't know if it's twins or triplets, but we do know if it's one kid or two kids. And the gender of the baby is going to be unknown. So now the gender of the baby can be 3 possible values: male, female, or unknown. And the plurality can be single, twins, triplets, quadruplets, quintuplets, but also multiple plus. So that's the basic thing that will appear in our data. And we create that pandas data frame, and we basically go ahead and write it all out. Okay? So at this point, if you go ahead and look at here, there's no, we haven't run this yet. So I can go ahead and run all the cells, and at this point, all of the cells will get run. At the very end, I will basically have my CSV files that I can now use for the next step, which is to basically train my TensorFlow model. Okay. So let's move back here, and now I'm going to basically move fast because I think you get the idea of how you walk through this. Okay. So one of the things that I kind of glossed over as I went through was that the way I split my data was that I didn't use rand. Instead, what I did was that I used a hash. And the reason to use a hash rather than a rand is that in this data set, and this is going to be common with a lot of different data sets, is that the rows are not actually independent of each other. If you have triplets, you have 3 babies, so you have 3 rows in your data, and those 3 rows are for the same mom. So it's the same number of gestation weeks, the same mother's age, the same everything. So they're not really independent rows. And you don't want to actually put those rows in, like one of those rows in training and another of the rows in evaluation. So what we do is that we make a hash of the row and we divide based on the hash. Okay. So we've now created our sample data set. The next step is to build the model. To build the model, the thing to realize is that there are 2 types of features in our data. We have dense features and we have sparse features. Dense features are features like the price, which is a continuous number. A sparse feature is a categorical feature like an employee ID, or the gender of the baby, is it male, is it female, or is it unknown? That's a categorical variable. So you have dense variables and you have sparse variables. And deep neural networks are really good for dense, highly correlated data because of the way they work with adding and subtracting data between layers. But on the other hand, sparse networks are really well suited to linear models. So if you have sparse features, you want to use linear models. If you have dense features, you want to use deep neural networks. But in this case, we have both. So what do? We use what's called a wide and deep model, where we take all of our sparse features and we put them into the wide part of the network, and we take all of our dense features and we put them into the deep part of the network. And the way you do this in TensorFlow is to use what is called a DNN linear combined classifier. So we're basically going to do this, and we're going to take some of our features and say these are our linear features and these are our DNN features. So let's go ahead and take a quick look. And in this case, what I'll do is I'll just step through the code on GitHub itself. Okay? But you can basically do this. You can run the code and you can train the model. So here, as before, you change your bucket, your project. And having done that, here's the TensorFlow code. We import TensorFlow. We say my data set contains these CSV columns. The weight in pounds is the baby male, the mother's age, the plurality, and the gestation weeks. And what we want to predict is the weight in pounds. And having done that, to read the data set, I'm going to basically go ahead and glob all file names. Globbing is basically putting a wild star, like an asterisk, right? So basically go ahead and reading all the files that have a particular prefix, because in reality, we will not be reading one file, we'll be reading a set of sharded files. So I'll be able to say train star. So having done that, I say this is a text data set, read it line by line, and decode the CSV. How do I decode the CSV? I take the CSV, and these are my columns, right? So basically, those are my defaults. That's my columns. So for each of them, take out the label because that's not a feature. So you have your features, which are one set of columns, and you have the label column, which is this one column in the original data set. So having done that, then go ahead and shuffle the data. Shuffling is a good thing to do in distributed training so that each worker gets a different copy of the data in essence, or is processing a different slice of the data at the same time. And you basically go ahead and repeat the data as many times as you need, and that's how you read the data. And now we basically say, given our data, how do we form our wide columns or our deep columns? Well, we basically say that the is male is a categorical column, mother's age is a numeric column, plurality is a categorical column, and this is the vocabulary, and the gestation weeks is a numeric column. So you basically specify what type of column it is, and that's our input data. And what I'm now doing is that I'm going to take my common columns, my numeric columns, and do what is called bucketizing. I'm going to discretize them to basically put them into bins. And in this case, I'm just putting them into bins of 15 to 45 in steps of 1. And then I'm going to do the same thing for the gestation weeks. And now my wide columns are the is male and the plurality. Those are both sparse, but also the discretized numeric columns. And having done that, now this is kind of where TensorFlow comes in really handy, is that you can do all these very sophisticated things. So sure, I've discretized it, but now I'm going to basically go ahead and do my feature crossing. And I'm going to feature cross these extremely sparse data to basically create, in effect, something like 20,000 new columns of feature crosses. I can afford to do this because my data set is very large. So having done that, I then do dimensionality reduction to a set of 3. Now the question is, do you need to do all this? If I didn't do any of these things, if I just took my raw data and I did it, I would lose about 30% in RMSE. So I get about 30% improvement by doing some of these sophisticated feature crosses, etc. And then I basically create my deep column. So I have my wide and deep. And then I can train and evaluate by creating a DNN linear regressor with the wide columns, with the deep columns, and then saying what it is I need to do for training. I'm going to read train.csv. What do I need to do for evaluation? Evaluate on eval.csv. So that's pretty much it. And I do one thing else, and this is something that a lot of people don't do, but a very good thing to do, something that you want to get to the habit of doing because it's going to be useful for every step after this, is that I also export the model. The reason to export a model is to basically take my model that I've trained and put it into a form where it can be quickly wrapped up and used for production, right? So I basically export my model, and when you're exporting a model, you need to think about, remember I talked about the REST API by which you access it? So here's the things that someone is going to give us in that REST API. They're going to give us the is male, mother's age, plurality, and gestation weeks. What does this look like? Right? It basically looks something like this. Somebody would be able to go into and create an application that looks like this, where that's the mother's age, this is the number of gestation weeks, and I expect that it is twins, both of them are male, and go ahead and predict. Right? So that's essentially the idea that we want to do when we are basically creating our TensorFlow model. Okay? So having done that, the next step, okay, is to pre-process the data with data flow. So we've created a TensorFlow model, it's been developed. The next step is to operationalize the model, is to take that model and operationalize it. Now this model that we've created is ready to go, except we don't have the full data yet. Now, the way we created the small data set before was to use pandas. Pandas is fine for experimenting, but if you want to operationalize your workflow, you want to make it repeatable, you want to have it deal with streaming data, you want to do your pre-processing not in pandas, but with something that's very scalable, something like Apache Beam. So that is going to be our next lab. And so the idea is to basically write this Apache Beam pipeline and lob it off to Cloud Dataflow, which is a service that will run this for us. It will auto-scale all of these predictions, and it will basically give us a number of things that are running. Okay? So we are now here on to the next notebook, okay, which is on pre-processing, and I'll skip to the key part of this notebook. And the key part of this notebook is that we are reading from BigQuery, we are reading the data from BigQuery, and we are doing the same things that we did in Pandas, except that we are now doing it in Apache Beam so that it can also work on streaming data. So imagine that you have data about births coming in from all the clinics in the country. As they are streaming into PubSub, you can read them, you can do this pre-processing, and then you can stream them out to your database, right? So we are basically creating a no ultrasound and a with ultrasound. And if it's no ultrasound, the gender is unknown. And then we're basically going ahead, and if the plurality is greater than 1, it is multiple. And I'm also, right, when I go ahead and do the query, I do the filtering. Is a weight in pounds greater than 0, etc. Okay? So we basically go ahead and do this, and we lob it off. Now, once you run this notebook, it will lob off the code into Dataflow. A few minutes later, you will basically have your large data set that's been created on, in this case, 5 nodes. In this case, actually 15 nodes, right? The current CPU is 15. So it just basically goes ahead and does it on how many ever workers you specify. Okay? And having done that, the next step is to train on ML engine. Again, next notebook. Okay? And the key point here in terms of training is very, very, very straightforward. You have your code. You basically tell ML engine, here's my code. It exists in this Python package. Please train it for me. That's pretty much it, right? You run a single command. It basically lobs it off, and it creates the machines. If it's on a GPU, it basically attaches GPUs to those machines. It does the training, and the trained model shows up on cloud storage. And once a trained model is on cloud storage, even while it's training, you can do your monitoring, etc. Then you deploy it. Deploying again, last notebook. To deploy it, you basically, it's again just a single command line call. Again, once you write a TensorFlow model, everything after that is essentially just single command line calls. You basically say, gcloud ML engine, please create a version of this model from this TensorFlow. And then once that's deployed, anytime it receives a JSON of this form, it basically goes ahead and sends back a prediction, which is why, right, something like this just works, right? So we can say the mother's age is 30, there's 6.2 pounds. If it's a single child, what is a prediction? That's 7.9 pounds, etc., right? Boom, boom, boom. You're basically getting predictions back because you've essentially deployed it. Okay? So and that's pretty much the end-to-end process of going ahead and building a model. So bottom line, explore your data, create your sample data set, create your TensorFlow model, and then operationalize it using Dataflow and using ML engine. Okay? And I'll skip this part. That's just building a web application. And with that, we will basically just stay tuned for a live Q&A, and we'll be back in less than a minute. do that. Okay, full screen on the questions. All right. Okay, so questions here. First question, is there a way to do this without using Data Lab? Can I use my own Jupyter build? Absolutely, right? So Data Lab is actually an open source thing. So let's go ahead and do GitHub and search for PyData Lab, which is the project that's in. And PyData Lab is a package. So you can basically go ahead and do a pip install of PyData Lab within Jupyter, and then you will have all of these capabilities that I talked about, all of the connections to BigQuery and ML Engine, et cetera. So that's all you really need. So go into the Google Data Lab project. Data Lab is the full notebook itself, but PyData Lab is the library that this thing uses, and this is a pip installable package. So you can go ahead and install it from within Jupyter. So if you're using your own Jupyter build, no problem at all. You can still do all this. Next question. Why did you use Cloud Dataflow to do the pre-processing? What are my other options? I think, like, in particular, can I use something like Spark? Absolutely, right? The reason I used Cloud Dataflow is because I always think about streaming, and streaming to me is the limit of where things are going to go. Anything that you're doing in batch today, people want to do things faster and faster, and the limit of that is that you want to do it as the data comes in. And the nice thing about doing it in Dataflow is that it's the same code that works on both batch data, historical data, and newly arriving data or streaming data. But you could do this in Spark. The only problem is that you will have to write it twice, once for batch, once in Spark streaming. Third question, how much does all this cost to do on Google Cloud? Not very much, actually. The Dataflow job to go ahead and data set was about maybe $2 or $3. The ML engine to go ahead and do the entire training cost me maybe about $8 or $9. I think you could do this entire workflow end to end in under $20. And of course, we have a free trial offer. So go to Google Cloud Platform, sign up for the free trial. You get $300. So perfectly possible for you to go ahead and do all of these code labs without spending any.